Good morning. I'm Zhenkai Zhang. I will present our work, Invalidate+Compare, a timer-free GPU cache attack primitive. As we know, GPUs have become increasingly popular, and they are needed by various applications, ranging from graphics rendering to deep learning. Despite the common adoption of GPUs, their security implications, especially from the hardware perspective, have not been thoroughly studied. As an outstanding example, information leakage through GPU cache is extremely underexplored compared to that of CPU cache. However, we believe that more attention should be paid to this research because many tasks running on a GPU actually involve sensitive information. Here, we study cache side-channel attacks on NVIDIA GPUs. Certainly to this end, a level of understanding on their cache properties is necessary. Let's first take a look at what properties we have known for sure. We know that NVIDIA GPU cache hierarchy consists of two levels. L1 cache is private to each basic compute unit called SM, standing for streaming multiprocessor. And L2 cache is the last level cache shared by all the SMs. NVIDIA documentation states that the load instruction brings data into L1 and L2 caches by default. So we can infer that L2 should not be exclusive. Although not explicitly stated, we can also find evidence to suggest that the cache line size is 128 bytes. An interesting property revealed in the NVIDIA documentation is that their L1 caches are not coherent. This means writing into a memory block in one SM's L1 will not affect other copies in other L1s. But for mounting powerful cache attacks, we need to understand more, especially the policies that dictate GPU cache operations. And we will leverage a GPU cache maintenance instruction named discard to achieve this. The discard instruction was introduced in the Ampere generation, and it is designed to facilitate the removal of GPU cache lines. Here's the syntax of the discard instruction. Aside from the address, we also need to specify the cache level and the number of bytes. Interestingly, the level can only be specified as L2, and the size must be 128, which is the cache line size. The discard instruction is similar to the x86 CR-flush, but with a little bit different semantics. According to their respective documentations, CR-flush removes the cache line from the entire cache hierarchy, but discard is only mentioned to remove the cache line from L2, which is the last level cache. Second, CR-flush writes dirty cache lines back to memory, but discard does not write any data back to memory, even if the cache line is dirty. For our study, we use the following 5 very recent GPUs, covering both consumer-grade and server-grade models. For a better understanding of the discard instruction and also the inclusion policy of L2, we perform the following experiment. Let's assume there is a block B in GPU memory whose initial value is 0. We let two SMs, X and Y, load B into the cache hierarchy. Next, we let X write 1 into B and let Y write 2 into B. Here we use a star to mean an indeterminate value where the reason will be mentioned later and is kind of irrelevant here. We then let X execute the discard instruction on B to remove it from L2. After that, we have X and Y read B again to check the value. We observe a consistent result across all the GPUs, which is X gets 0 and Y gets 2. From this, we know that L2 is non-inclusive, otherwise Y should have obtained 0 instead of its private copy. We can also find that discard removes the cache line from L2 and also from the L1 of the SM issuing the discard instruction, which is not specified in the documented semantics. We can also know that L1 caches are not serviced from lower levels of GPU memory hierarchy rather than the sibling, actually are serviced from low levels of GPU memory hierarchy rather than the sibling L1 caches. If this were not the case, X should have obtained 2. We have designed several other experiments taking advantage of the discard instruction and L1 incoherence. We find that NVIDIA GPU's L1 is right through, which explains the previous star because the final value really depends on the order of the writes. And L2 is a write-back cache. We also prove that when a write operation misses in L1 or L2, the corresponding block is fetched and put in a cache, which is known as the write allocate policy. More interestingly, we discovered that GPU context switching automatically flushes all the L1 caches, but not the L2. Because of the auto-flushing behavior, L1 will not be a problem, even though L2 is non-inclusive. So we can focus on the dynamics of replacement in L2, which is a 16-way set associative cache. An interesting finding is that L2's 30 cache line ratio is at most 50%. We discovered that using 7 stores and 9 loads to prime a cache set is deterministic. However, the L2's replacement policy is quite unusual. Basically, if the least recently used cache line is dirty and gets evicted by a load, the least recently clean one will also be evicted. Fortunately, within the group of dirty cache lines and the group of clean cache lines, the least recently used policy is employed, which suffices for the scope of this study. Based on the learned properties, we propose our Invalidate+Compare primitive. Now let's see its main idea. Let's assume there is a block B in GPU memory whose value is alpha. We perform 7 stores and followed by 9 loads to prime the L2 cache set where B is mapped. The first store we perform is to write a new value beta into B. After some time, we execute the discard instruction on B and then read it back to check the loaded value. If the specific cache set has not been accessed by any other running GPU program, we will get the original value alpha back. Otherwise, access to this cache set will evict the dirty cache line corresponding to B. And we will get the new value back when B is loaded from memory. So this primitive allows us to check if a cache set is accessed or not in a timer-free manner. However, to effectively use this primitive in practice, several challenges need to be addressed first. The first one is how to synchronize the primitive with GPU context switching. This is due to the fact that GPUs execute concurrently running programs not simultaneously, but in a time-sharing manner. So we need to prepare the target cache sets and wait for switching to the victim's context. After the context switched back, we check the cache sets. Our solution to this problem is built on several L1 cache properties. We dedicate an SM to continuously incrementing a flag variable. Since L1 is right through, it will continuously update L2. For other SMs, after they prime the cache sets, they write 0 to the flag variable and then repeatedly check it until the flag becomes non-zero. But due to L1 incoherence, the flag will stay at 0 unless it is invalidated in L1 and fetched from L2. Now, L1 auto-flushing comes into play, which is triggered by GPU context switching. So when the context is switched back, the SPI SMs will break out of the loop and proceed to check the cache sets. Another challenge arises because during a time slice, a large number of GPU cache sets may be accessed. As a result, just deducing if a GPU cache set is accessed or not may not suffice. To address this problem, we propose a revision. Instead of just checking whether a cache set is accessed or not, we measure the degree of contention in a cache set. Basically, we perform the invalidation operation across all the 7 written addresses and identify the first one that is not evicted through comparison. We then use the position of that address to encode the intensity of contention in the corresponding cache set. We demonstrated the use of our primitive through two case studies. In the first one, we mount a website fingerprinting attack. Web browsers use GPU's assistance for rendering web pages, which makes GPU cache access patterns web page dependent. Here's an example of browsing 3 websites in Chrome. These memory grams are captured using our primitive on an RTX 4060. We can see these memory grams can be used to distinguish between those websites. Due to the time limit, let's just show the result of a 5-fold cross-validation conducted using memory grams corresponding to 50 websites. From the results, we can see the performance is very good. In the second case study, we want to recover more fine-grained and sensitive information. To this end, we focus on the keystrokes made by user on a virtual keyboard. When the key is pressed on a virtual keyboard, it exhibits some local visual effects like shading the surroundings of the key. The desktop system just re-renders that particular area for efficiency. That means only part of the desktop environment's GPU buffer associated with the dirty region is accessed. So pressing different keys leads to access different GPU memory addresses, which produces distinguishable traces in the GPU cache. Here's an example of memory grams captured using our primitive on RTX 3080 for pressing A and B twice. You can observe some differences, but for a better effect, we show a differential view to highlight the differences between A and B and the consistency in the differences. We evaluate if we can extract a user's system login passwords entered via the virtual keyboard. 4 common passwords are used, and we can indeed decipher many segments of these passwords. Due to the time limit, I skipped many details. If you are interested in our work, welcome to read our paper. Okay, to sum up, we have unveiled certain previously unknown characteristics of NVIDIA GPU caches for the first time. We have introduced a timer-free GPU cache attack primitive, and we have showcased the use of this primitive through 2 case studies. Okay, thank you.